Hello, welcome back to another video. Today we're going to be talking about the transformation of functions. Before we talk about the rules for transformations, I want to review the parent functions first. The first one, which is f of x equals x, represents a linear function. That graph just looks like a straight line going through the origin. The next one, the absolute value of x, that's the absolute value graph. That one looks like a letter V. With the vertex at the origin. The next graph is a quadratic graph represented by the equation f of x equals x squared. The quadratic function makes a parabola or a U-shaped graph. The next one is the square root function. That one has the vertex at the origin and then goes out that way to the side. The next one, x cubed, represents a cubic function. And that one looks like this. The next one is the cube root function. Similar to the cubic, but kind of on the side like this. The next one is the rational function. This one has a vertical asymptote and a horizontal asymptote at x equals 0 and y equals 0. And that graph looks like this. The next one is the exponential graph. That one has a horizontal asymptote at y equals 0. And the graph looks like this. The last one is the natural log. That one has a vertical asymptote at x equals 0. And it looks like this. Okay, so here are the 9 parent functions. There's more, but these are the basic 9 that we'll be talking about for this lesson. Okay. To graph the equation of a function, you first have to determine all the reflections. Then you're going to determine the translations. And then you're finally going to graph. Okay. So here are the rules for the transformations. You can have a vertical or horizontal shifts. So if at the back of your parent function you have a plus d or a minus d, that means that you're going to be going up or down that many number of units. If you have plus c or minus c on the inside of the parent function, you're either going to be going left or right. If you have a negative outside of the function, you're going to reflect over the x-axis, but if your negative is inside, then you're going to reflect over the y-axis. And then for a is being multiplied outside of the parent function. If a is greater than 1, you're stretching vertically. If a is less than 1, you're compressing vertically. B is inside, being multiplied inside of the parent function. If b is greater than 1, you're compressing horizontally by a factor of 1 over b, and if b is less than 1, you're stretching horizontally by a factor of 1 over b. So it might help to see the vertex form of the functions. So usually it would be negative a parentheses b parentheses, negative b parentheses x minus c squared plus d. So the parent function is basically this part right here. So the the y-axis reflection is inside the parent function, the horizontal stretches or compressions are inside, and left and right is also inside of the parent function. Now the parent function can change depending. This one happens to be x squared. We can change it to be x cubed. We can change it to be the square root. We can change it to be the absolute value. If we got rid of this, it would be linear. So you have a lot of different options here. You can make it the cube root. But notice that all of this stuff always appears inside of the parent function. The x-axis reflection and the vertical stretch and compression are outside, as well as the up or down. So that might help you with the translations and identifying the transformations. All right, so let's start with a few examples. We're going to graph the following functions, and then we're going to determine the domain and range for each function and provide them in interval form. So the first one is f of x equals x plus 1 squared minus 3. The first thing we can say about this is that the parent function is a quadratic graph. You can see that we have the bones of the x squared. So if you had got rid of this stuff, you see you have the x squared. So that's a quadratic graph. Okay, now c happens to be on the inside. The value of c here is -1. So I know that it looks like it says +1, but notice that earlier we said that the vertex form has a -c. So basically what's happening to get this, so let me bring this up here. In order to get +1 squared, it had to have originally been x minus -1 squared, because this minus is this minus right here, this one. Oh, there's like red stuff everywhere. I don't know if you can tell anymore. But yes, there's already a minus here. So if in order for it to become a plus, it had to have been another minus that would connect to be a +1. So basically everything on the inside is always the opposite of what you think it is. So if it says +1, it's actually -1. And so if you're going towards the negative direction, you're going to be going left 1 unit. Okay, now outside of the parent function, so here's where the parent function ends after the squared. After that, we have a -3. So that means that the value of d is -3, which means we're going down down 3 units. Okay, so if the original parent function has a vertex at 0, 0, we can grab that vertex and go left 1 and down 3 units, and that is where our new parent function will be. So you can see the translation there. So I'm going to go left 1, down 3, and I'm going to draw a parabola because this graph is quadratic. And now I know that the new vertex is at -1, -3. So I can use that to determine the domain and the range. So the domain I see goes from -infinity to +infinity, and the range is from -3 to infinity. But the -3 is an included point, so I'm going to be using a bracket there. All right, next example, f of x equals 2 minus the square root of x minus 1. The first thing I want to do is rewrite this so that it's in vertex form. So this like random 2 needs to be on the back because that's going to be the value of d. Now that negative inside doesn't correspond to the minus, it's not -2. This is a +2 minus the square root. So that minus is going to stay with the square root and the +2 will go on the back. So from here I can start identifying the transformations. So that negative in the front tells me it's a reflection over the x-axis. That 1 on the inside, C is +1. So remember, it's always the opposite of what you think. So if it says -1, it's actually +1, meaning you're going to the right 1 unit. And then on the back, we have D equals 2, which means we're going up 3 units. Sorry, up 2 units. Okay, so if the original square root, sorry, I didn't even say that the parent function here was the square root. So you can see we have the square root of x. The original parent function looks like this. If we reflect it over the x-axis, that means it's going to be down here. Okay, so from the bottom one, that's the one I'm going to move right 1 and up 2, and it's going to be like this. And that one will have the reflection and the translation right up in 1, 2 units. And so it's going to look like this. And that vertex is going to be 1, positive 2. Okay, so that domain is going to be coming in from the left-hand side. We start at positive 1 and we go all the way to infinity, and positive 1 is going to be in a bracket because it is a defined point. And then the range coming from bottom to top, this goes all the way down. So from negative infinity, and then it stops at positive 2. And again, bracket on the 2 because it is an included point. Okay. So that's that page. Moving on. I want to show you stretches and compressions. The formatting of my page got a little wonky, but I wanted to show you using the sine graph. So sine of x, showing you the differences between vertical stretches and compressions and horizontal stretches and compressions. So I'm going to open up a graph, and I'm first going to type in sine of x so you can see what the parent function of sine x is. Okay, so there is sine of x. Now let's graph the next one, which was 2 sine of x, and let's see what happens when we stretch it. Oh, how do I add a new graph? Okay, there we go. So the black one is the original sine of x, and you can see the 2 sine x is getting pulled in the vertical direction, so it's the maximums and minimums are going a little bit higher than they were before. So the original ones only go from negative 1 to positive 1, but the red ones go from negative 2 to positive 2. So they go higher and lower than it previously did. Let's observe what would happen if we put in 1/2 sine x. Okay, so you can see the pink one, the extrema are shorter than they were before. So now it only goes from negative 1/2 to positive 1/2. So that's a vertical compression where it's kind of getting squished up and down. So I'm going to sketch these on our notes. So the sine graph, remember that only went from positive 1 to negative 1. So I'm going to make sure that my lines stay between negative 1 and positive 1. I feel like it's not very good. Hold on. I guess that's better. But then the 2 sine graph went all the way to positive 2 and all the way to negative 2. So that one is kind of longer like this. So it got pulled vertically. Versus the 1/2 sine only went to negative half and positive 1/2. So it's kind of more like this. Okay, so you can see the differences there. So the purple one, again, it existed between negative 1 and positive 1. When it was stretched, it went all the way to negative 2 to positive 2. But when it was compressed vertically, it only existed between negative 1/2 and positive 1/2. So you can see where it's being stretched and pulled up and down versus pushed together up and down. Okay, now let's do the same thing, but for horizontal stretches and compressions. I'm going to go back to the graph. I'm going to type in again sine of x. So this is the original one. Now, if I were to type sine of 1/2 x, this is what happens. So you can see the space in between the extremas is kind of getting pulled outwards. So there are less cycles happening. They're more spread out. So you can see if I zoom out a little bit, they're more spread out. So for example, on the first quadrant on the green, we have 1, 2, 3, 4 extrema versus only 2 when it was being horizontally stretched. Now let me add sine of 2x. Now you can see that there are more cycles, so it kind of goes a little bit faster. So basically, if it's being stretched horizontally, the cycles are more spread out. If it's being compressed horizontally, the cycles are more frequent. So let's sketch that over here. So hold on. It's a very rough sketch, but that's kind of what it looks like. Now for the stretch, it's kind of more like this. So there aren't as many. So you see how the space between here and here, like this, is smaller versus this is longer. So the space between the cycles is shorter in the original and longer when it's being stretched horizontally. Now the opposite is true for horizontal compression. That one just occurs a lot more often. So it's kind of more like this. Okay, so again, let's review. So the space between here and here, that's the normal one. If it's being stretched, you can see that it's a lot longer. And if it's being compressed, you can see the space is a lot shorter. So it allows more cycles to show up more frequently. Okay, so those are the differences between horizontal stretches and compressions versus vertical stretches and compressions. Let's go on to another example. Provide a verbal description of the transformations applied to f of x to obtain g of x. So we see the parent function is a quadratic. They tell you that f of x is x squared. And then we have 3 minus 6 times x minus 2 squared. So again, this random 3 needs to be put to the back. We know that it's not an a. It's often confused for a, but a and b are multiplication only. Okay, if a number is being added or subtracted, it's either going to be a D or a C. It's D if it's on the outside, C if it's on the inside, okay? But A and B, do not confuse them. They have a multiplication symbol in between them. So unless something is being multiplied, it will not be A or B, okay? And that 3 is not being multiplied. We have a minus 6x squared. That's not 3 times 6x, so we're not going to think that's A or B. Okay, that has to be D. So I'm going to rewrite this to be negative 6 x minus 2 squared plus 3. And again, the sign of the 3 comes in the front, and since there isn't something there, it has to be positive. Okay, so we can start applying the transformations in order. So the first thing we see is that negative. The negative appears outside of the parent function. Notice that it's outside, so it'll be a reflection across the x-axis. The next thing we see is a 6. When the number is outside of the parent function, that'll be a. If a is greater than 1, you vertically stretch by a factor of that number. So vertical stretch by 6. The number on the inside is 2. That would be a C. And since it's minus 2, remember it's the opposite. So instead of negative 2, we're going to have a positive 2, meaning we're going to the right 2 units. And then on the back side, we have D equals positive 3, meaning we go up 3 units. Okay, so that's that example. The important thing here is that you rewrite the equation. All right, question number 3. Given the graph of f of x, answer the following questions. What is the parent function? This would be the absolute value. You can see it looks like the letter V. And the absolute value graph is f of x equals the absolute value of x. Okay, is the graph shifted left or right? If so, by how many units? So we can see if it usually starts at the origin, it got shifted to the left 2 units. And then was the graph shifted up or down? So if it usually starts at the origin, you can see that it went down 1 unit. Was the graph reflected across the x-axis or y-axis or not at all? If it had been reflected across the x-axis, so if this is the original, it would have looked like this reflected across the x-axis. The y-axis reflection, it's basically the same. It's already reflected, really. But there was no reflection because it has to be along the y-axis. It has to be symmetric. But you see that across the y-axis, we only have this little part versus this big part. So that's not symmetric. So we're going to have to say not at all. It was not reflected. It was just moved left 2 and down 1. Okay, is the graph stretched or compressed vertically or not at all? In order to determine that, we have to see what the slope is of the original and what the slope is of the one that they're asking us about. So I'm going to sketch the parent function. Hold on. Okay, so that's what the original absolute value graph looks like, the parent function. And now we're going to determine the slope. So if you remember from algebra that the slope is equal to rise over run. So starting from the origin, we go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. So the slope for this one is 1 over 1, which is just 1. Okay, so the slope is 1. Now let's do the same thing for the second one. So we have to go up 2 over 1, up 2 over 1, and so forth. So the slope is 2 over 1, which is 2. So you can see it got stretched vertically. You can see that the steps got a lot longer. Here they were shorter. So it got stretched vertically by 2. And again, we determined that by finding the slope of the line. So vertical stretch by 2. What is the equation of f of x? Okay, let's put it all together. You know, the absolute value is the parent function. But outside of the parent function, we got to put that vertical stretch of 2. Inside, we're going to put the left or right. Remember, if it's left, you're technically going -2. So the equation, the vertex is -2, -1. But instead of the negative, you're going to put a +2 because it's always the opposite sign. And then the down one would be a -1. Okay, so this is the equation of the graph. All right, moving on to some more examples. Rewrite in transformation form and state the transformation. Okay. So the first thing we have to do is rewrite. So notice that the 2x and the 8 here are switched. So we're going to rewrite it so that it looks exactly like the vertex form. Okay, another thing that's important is that your x value has to be alone with a coefficient of 1. So when I had put this vertex form here, you can see that the b was factored out and your x always has to have a coefficient of 1. You can see that here as well, that your coefficient of x is always 1. So whatever b is, we're going to have to factor it out, and that is very, very important. Otherwise, you're going to get the wrong c value. So factoring out that coefficient of -2 on the inside, if I were to take that out, I would get -2 and then in parentheses x minus 4 and then outside +6. If I were to redistribute this -2, I would still get -2x plus 8. But we have what we need, which is that x has a coefficient of 1 inside of this factor. Okay, it is very important. If you had not factored, you would have said left 8 versus right 4, which is the correct transformation. Okay, so let's list these in order. So that negative that we see first, this negative right here outside, means that we're reflecting across the x-axis. The next thing I see is a 3, which is outside of the parent function, meaning we're stretching vertically by 3 because a is greater than 1. Okay, the next thing I see is this negative. A negative inside of the parent function means that we're reflecting across the y-axis. Then I see a b. So b is 2. If b is greater than 2, that means you're horizontally compressing. And the b is always the reciprocal. So instead of by a factor of 2, it'll be by a factor of 1/2. And you can look at that again in the rules that for b, it's always a factor of 1 over b. So if our b was 2, it'll be a factor of 1 over 2. Okay, so make sure it's the reciprocal. Everything on the inside is the opposite of what you think it is. Okay, then we have c. So c is +4. Remember, it's the opposite. So we're going to the right 4 units. And then at the back, we have D, which is 6, meaning we're going up 6 units. Okay, so all of the transformations, reflection across the X, vertical stretch by 3, reflection across the Y-axis, horizontal compression by 1/2, right 4, and up 6 units. Okay, let's do another one. We have 1/2 times log of 10 plus 1/2 x minus 4. So we'll start the same way. We're going to rewrite the inside so that the 1/2 x comes before the 10. And then the next step is to factor out whatever is being multiplied by x. In this instance, it was a 1/2. And then 1/2 times 20 gives you 10. And again, you can see the importance of factoring something out. If you did not factor out this 1/2, your answer would have been wrong because you would have said left 10 instead of left 20. So it is very important that you factor out the coefficient of x. Okay, so starting in order, we have a 1/2. This is the parent function. The parent function here is a logarithmic function. So the 1/2 is outside being multiplied. So a is 1/2. And if a is less than 1, it'll be a vertical compression by 1/2. Okay, the next thing we see is another 1/2, but this one is inside of the parent function. So the parent function being log and the 1/2 is inside. So this one will be b. When b is a fraction, meaning it's less than 1, you're going to be horizontally stretching. And again, by the reciprocal, so the reciprocal of 1/2, if you flip these around, you get 2 over 1, which simplifies to just 2. So it'll be a horizontal stretch by 2. On the inside, we have C, which is negative 20, meaning we're going left 20. And then we have D is negative 4, so we're going down 4 units. Okay, so this one had a vertical compression by 1/2, horizontal stretch by 2, left 20, and down 4. Okay, let's do some more examples. Here we have two functions, f of x and g of x. And some of them, they want us to vertically stretch, horizontally shrink, etc., etc. Okay, so let's say I make f of x this blue color and g of x pink. Okay, so they want us to vertically stretch f of x by 3. So if we look at the rule for vertical stretches, that is a times f of x. So I'm going to rewrite a times f of x down here on my paper. And that vertical stretch by 3 lets me know that a is 3. So I can write 3 times f of x. Okay, so that's what the rule is going to be. And then f of x is right here, which is equal to x cubed minus 16x. So I can replace the f of x with the actual equation of f of x. Okay, and then from there I can just simplify. So I'm going to distribute that 3. So we'll have 3x cubed, and then 3 times negative 16 is negative 48x. Okay, and this would be the final answer, 3x cubed minus 48x. Let's try another one. Horizontally shrink f of x by 1/2. Okay, so horizontally shrink. And we go back to the rules. Horizontally shrink is the same as horizontal compress. That means that it's going to be a b and it'll be inside. It's always the reciprocal. So if it says by a factor of 1/2 and the factor is always 1 over b, that means that b has to equal 2. Okay, so I'm going to rewrite f of bx. Okay, and we said by a factor of 1 over 2, and the factor is always 1 over b, which means that b has to equal 2. So I'm really doing f of 2x. Now, what am I going to do with that 2x? This one is different than a. So on a, when you have something outside, you can distribute it. That's outside. But if it's inside, you have to plug in to every place that there is an x in the function of f. So if f of x is x cubed minus 16x, in these two x's, I'm going to plug in this x right here. And make sure you use parentheses. Okay, so you can see that this function and this function are exactly the same. We have f of x equals x cubed minus 16x, but in the three places that there used to be an x, which were here, here, and here, those three have been replaced by a 2x. And then from here we can just simplify. So 2x cubed. So remember 2x cubed, anything cubed means you're multiplying it by itself 3 times. So this is really 2x times 2x times 2x and then minus 16 2x. Okay, so we got 2 times 2 times 2. So 2 times 2 is 4 times 2 we have 8. And then x times x times x is x cubed. And negative 16 times 2 is negative 32x. So our final answer is 8x cubed minus 32x. Okay, so again, just remember the difference. If it's outside, you distribute. If it's inside, you're going to plug in. Okay, let's try another one. Reflection across the x-axis. This is for g of x. If it's x-axis, it's going to be, the negative will be outside of the parent function. And this is now for g of x, so I'm going to replace g of x where I wrote g of x over here. But I'm going to keep that negative that I had before, so I can actually reflect it. So I'm going to rewrite the equation of g of x. Okay. And now we're going to distribute that negative. Now the important thing is when you're distributing a negative with a fraction that you only distribute it to either only the numerator or only the denominator, you absolutely cannot distribute it to both. So let me show you why. If we have negative 7 over 10, for example, we can have the negative outside, or we can distribute the negative to the numerator, or we can distribute the negative to the denominator. Okay, so notice the negative can be outside, on the top, or on the bottom. All of these fractions are still negative. They are all still equal to negative 7 over 10. Now, if you had instead tried to distribute this to both the top and the bottom, you would end up with a negative 7 over negative 10, which means that the negatives will cancel out, leaving you with a positive fraction. Okay, so again, it's important you only do one, or the top or the bottom. But if you do both, you're changing the sign of the fraction from a negative to positive, so you don't want to do that. Okay, so on this problem, I'm only going to distribute it to the numerator. You could do the denominator if you want to. So if I distribute that, I'll have negative 5x plus 9, and then you leave the denominator alone. Okay, so this will be the final answer there, negative 5x plus 9 over x squared plus 3. All right, let's try reflecting g of x across the y-axis. So if it's across the y-axis, the negative occurs inside of the parent function. So it'll be a negative x on the inside. Let me show you on the rules. Okay, so if it's a reflection over the y-axis, it's f of negative x. Well, this time we're doing g, so it'll be g of negative x, which is what I had written already. And remember, when you have something on the inside of the parentheses, that's where you're going to be plugging in to every x of that function. So I have 5 times negative x minus 9 over negative x squared plus 3. Okay, so let me show you. These two are exactly the same. They are exactly the same, except for the fact that every area that there used to be a positive x, I have replaced it with a negative x, and I just put it in parentheses, but aside from that, everything is the same. Okay, now I'm just going to simplify this. So 5 times negative x is negative 5x minus 9. Negative x squared, two negatives make a positive, so this will be a positive x squared plus 3. Okay, so the final answer is negative 5x minus 9 over x squared plus 3. Okay, a few more examples. Describe the transformations necessary to transform the graph of f of x into that of g of x. Okay, so we have a square root function here. So this is the square root function. We have a negative on the outside of the parent function, meaning that's a reflection across the x-axis. A is 3, which is greater than 1, so we're stretching vertically by a factor of 3. And then notice that the parent function ends right here. It is not also over this negative 1. So this negative 1 is outside of the parent function, so it'll be a d. And d is negative 1, meaning we're going down 1 unit. Okay, so reflect across the x, vertical stretch by 3, and down 1. Let's do number 4. This one is a cubic function, x cubed. We have a 3 on the outside. A is 3, vertical stretch by a factor of 3. And then on the inside, we have a positive 1. Remember, it's always the opposite sign, so it's actually a negative 1 going to the left 1 unit. Okay, so vertical stretch by 3, left 1. That looks ugly, sorry. Left 1 unit. Okay. 2 more. Transform the given function f of x as described and write the resulting function as an equation. So f of x equals x squared. Expand vertically by a factor of 3. Vertical means a, so we're stretching a by 3. And translate down 3 units means that d is negative 3. So we can put it together. Let's say g of x is equal to 3 and then x squared. We don't really need that parentheses. I'm actually going to take it off. We can just do 3x squared minus 3. That'll be our final answer. 3x squared minus 3. Now for number 6, it helps to know the vertex form of a rational. Which is a fraction with a variable in the denominator. So f of x is equal to a over b x minus c plus d. Okay, so it says compress horizontally by a factor of 2. Remember, the factors are 1 over b. So that really means that b is 1/2. Okay, because this is technically 2 over 1. And if you take the reciprocal of 2 over 1, that becomes 1/2. Translate down 3 units. Sorry, not down. Translate left means that c is negative 3. Okay, so I'm going to write this as g of x. Now, for the 1/2, notice that b is in the denominator, but I'm not going to put a 1/2 here. I'm actually going to multiply the whole fraction by 1/2, so it'll be like this. And that way in the front of the whole fraction, I have the 1/2. So it'll be 1 over 2, and then translate left 3 units will be x minus 3 in parentheses. Okay, and then I'm going to distribute the 2, and you end up with 2x plus 6. Sorry, 2x minus 6 as a final answer. Oh, wait. Yes, it was plus. Sorry. Yeah, so you put the opposite sign. So final answer is 1 over 2x plus 6. Okay, so these are all the questions I have to go over today. I would highly recommend that you review these rules and you memorize them. These will not be on your formula chart, so you need to know them like the back of your hand. So yeah, I hope that you learned some more about function transformations, and I'll see you in the next video. Bye.